All right, guys, so in the last section, one of the things that we did was we took a close look at Ohm's law and rewrote it in phasor form when the current going through the resistor was a sinusoid. And we found that Ohm's law, whether it's in the full time domain or whether it's in the frequency domain, when we turn them into phasors, they basically have the same mathematical form. We now want to turn our attention to a second passive element, the inductor, and we want to take a look at the sinusoidal response of it and turn the IV characteristics into phasor form. So here we're going to take a look at part 2, and this is the inductor. So suppose that we start with an inductor like this. It's characterized by an inductance L. And further suppose that we place a voltage across the terminals. We know that there's going to be a current which changes as a function of time going from the positive terminal down to the negative, like so. And the IV characteristics, the relationship between the voltage and the current, for the inductor are such that the voltage across the inductor is equal to the inductance times the time derivative of the current. Right? Now, this is fully in the time domain. Right? We haven't said anything more specific about the nature of the voltage or the current. But since we are working with sinusoidal sources, let's assume that the current that exists in this inductor is sinusoidal. So it has a magnitude, I sub m, and it is the cosine of omega t plus theta sub I. The I is just there to remind you that this is the phase constant for the current. Now, we can derive exactly what the IV characteristic is going to be, what the voltage function is going to be as a function of time, by taking this assumed form for the current and actually cranking it through the time derivative. So here, the voltage as a function of time is the inductance times the time derivative of I sub m times the cosine omega t plus theta I. Now, remember, when you take the time derivative of a cosine function, it is negative sine, right, times by the chain rule, the derivative of this, the time derivative, and the time derivative of omega t with respect to t is just omega. So this full derivative is minus omega L times the sine of omega t plus theta sub I. This is where I'm actually going to call on a trig identity. To help us along. And the trig identity tells us that if we happen to have the sine of some angle, just suppose that it's alpha, we can turn it into the cosine as long as we take this angle and we shift it by 90 degrees like this. So this identity is relatively easy to prove. Notice that this I can actually use up there. So this whole thing can be rewritten in the following manner. I have v of t is equal to minus omega L times the cosine of omega t plus theta sub I minus the 90-degree phase shift. Now, this is what's going to happen with sinusoidal sources. We're now in a position to actually take the phasor transform. So here we're actually going to take the phasor transform of this. And we're going to do this on both sides. Now, on the left-hand side, if you phasor transform the voltage as a function of time, well, that's just the phasor voltage. And the phasor transform of this portion, well, remember, here what we're going to do is we're only going to take the magnitude for the phasor transform. So The magnitude is this part, and we're actually going to take the phase angle, which is this part. So I can rewrite this whole thing as the magnitude omega L, times I totally dropped something. Let me put this back in with blue. Somehow or another, that little part got dropped. So let's actually put it back in. So this is I sub m, and that's I sub m. So we have omega L times I sub m. That's the magnitude times e to the j theta I minus 90 degrees, like this. Right? Now, I can keep on working with this in the following manner. I can rewrite this as minus omega L times I sub m, and I can split apart the portion in the exponential. The first portion is going to be e to the j theta sub I times e to the minus j times 90 degrees, like this. And let's actually take a closer look at what e to the minus j times 90 degrees is, right? So here, I'm going to look at e to the minus j 90 degrees. Notice that I can actually use Euler's identity on this. In the following manner. And I can rewrite e to the minus j times 90 degrees as the cosine of 90 degrees plus j times the sine of minus 90 degrees, like this. Right. And if you'll recall, the cosine of 90 degrees, well, this happens to be 0, right? Sine is an odd function, so I can pull out this negative straight out of the sine, in which case I get minus j times the sine of 90 degrees, and the sine of 90 degrees is not 0, this is just 1. So notice that this is the same thing as minus j. Now, the reason I'm doing this is so that this part I can use right there. So far what we actually have is that the phasor voltage is equal to minus omega L times I sub m times e to the j theta I, and we just found that e to the minus j times 90 degrees is minus j. Well, that minus sign, they cancel out, and we're left with j omega L. Right? And I'm going to go ahead and put in parentheses I sub m e to the j theta I, like this. So hopefully you can convince yourself that this part, this whole thing, can be reduced like this. Now let's take a critical look at what we have there. Right? Remember that theta I is the angle, the phase angle, or the phase constant for the current. And if I happen to have the magnitude of the current times e to the j times the phase angle of the current, well, that is by definition the phasor of the current. So here we identify I sub m times e to the j theta I. This, by definition, is the phasor of the current. So here, for the IV characteristics, for the inductor, I have the phasor voltage coming from here is equal to, well, we have j omega L times now this phasor current there, which we can rewrite like this. Like this. This was the portion that I actually wanted to get to. This is the IV characteristic of an inductor in the frequency domain. And one thing that I really want to impress upon you is that the voltage here is equal to a constant, because J, omega, and L are not changing times the phasor current. But we'll see how to use this later on as well.